walking. I think I was in Cambridge, and coach told me it's just 20 minutes from your hotel to the department. I was in one of these colleges. And then I started going. It became 25, 30, 35. So he was going fast. What? I'm okay. You're here, right? Okay. He's the student who put this in for me.
Oh, I see. I was just telling Professor Shahidi how, this kind of title is very dangerous. You never.
That's why I have the on.
If I saw a talk and it said Riemann hypothesis,
Yeah,
I
yeah,
would
you-
fully expect.
No, don't expect
Theorem
anymore.
one.
What I say conjecture, I would have said theorem.
Oh, I see. Ramanujan-Selberg-Shahidi theorem. Yeah.
I wouldn't put my name on it. That's fancy enough.
Yeah. Right.
Put a PDF on the internet with the proof. That moment.
It seems like people were now.
Yeah, it's what they. Yeah, that's
Yeah,
it.
I was just telling him.
I
Like,
kept
what
it
kind
all
of
the
title
time
is
for
this?
you.
It was ready for the 60th
Yeah,
birthday, and then this
I
whole
have to
thing
wait.
happened.
Yeah. It was supposed to be on Ramanujan, and somebody removed that on. For technical reasons, apparently. For the heading to fit or something.
Right. You couldn't fit on. It didn't
Yeah.
fit on the line.
That's right.
Yes,
That was the
that's what
argument.
happened. Peter likes this stuff,
Oh,
as
yeah.
I'm sure.
I mean, I chose this for him. I had other things to talk about.
Did the two of you ever actually work on a paper together?
No, we didn't, but we talked a lot.
I mean, yeah, I can
Because
see
Kim
that,
did, and it was Kim worked with him. Oh, we did this volume for the Park City. That's we co-edited. So that's a collaboration in the system of. You mean you remember this Park City 2002 summer school?
I wasn't at the Park
Okay,
City, but
yeah.
I was only a first-year grad student, so I was
Okay,
just fighting for
Fine,
life.
yeah, okay. So we co-edited that volume together. So that's a collaboration in some sense.
That's a lot of work. I mean,
It was a lot of work.
I
Especially if you want to get anything out of Bernstein. I mean, which we couldn't.
those are the
We
worst.
gave up. We couldn't.
I was in Michigan when Jeff Ligarius was editing his 3x+1 book. And for about 2 years, every day he would cry about how difficult it is to get people to do
Yeah, of course.
I think it made it.
Yeah.
Okay, good afternoon. I hope we've all had a productive and enjoyable lunch break. A great pleasure to be able to assist in this way. So we will have the great pleasure of opening the afternoon session with a talk by Fridun Shahidi, who will talk about the Ramanujan-Selberg conjecture.
Thank you. Well, it's a pleasure to be here to speak in honor of Peter, who I admire very much. And thanks a lot to the organizing committee for inviting me to this. Peter and I know each other for quite some time. We shared an office at MSRI in 1995, I think. We had that beautiful office in top floor. And director was passing by every day and taking a look and wondering about this office. As soon as we both left, he took that office as his own office. So Peter has had a really influential role in the development of analytic number theory, and it has been a great bridge between analytic number theory and the automorphic forms. He has been very supportive of all of us in this way. When Kim and I did this result, Peter was all over. He helped us. He suggested new problems, new applications. Every day he would send an email, and then he would write to us new things. And some of them we put in our papers, but some of them are folklore around. And whenever I talk somewhere, I talk about them. And I say, this comes from a letter Peter wrote to me. So it's an honor to give this talk. Many, many returns of good life and work, hopefully many, many more of that. So I chose this. Yes. It may fall. It's not easy to see with the. Is it good? Okay. Oh, I do this? All right, that's a solution. I'll do this. Well, it depends how hot I become. It may. Is it better now? Okay. Anyway, I chose this subject for this talk because I really love the subject, and I know Peter likes it, and he has contributed to it. And we just put a paper on arXiv with Cogdell and Tsai, and I will talk about it at the end, but that was something brand new, fresh. But I think I like to talk about this because there are some other ideas for more general group besides GL2 that I will discuss after this. Let me just go quickly over the basic facts on GL2. UTABI, let F be a normalized, maybe I can do it even from here. We let F be a normalized mass form for gamma naught of n, the Hecke group, the Laplacian, hyperbolic Laplacian, minus y squared, rho squared, x squared, plus rho squared, rho y squared. And we assume F is an eigenfunction for the Laplacian and for all the Hecke operators. Then, being an eigenfunction for delta, it is given by this. I think I'll stand here. It's better. Okay, it's hard to see this. Yeah, it's given. You can write it as 1/4, 1/4 of 1 plus s squared times f. And s is a complex number, which I will discuss in a minute. And then f being an eigenfunction for Laplacian and also for all the Hecke operators, we'll have an expansion, as you can see. It's a real analytic function, so as a function on upper half plane is going to be sum for all n different from 0, absolute value of n, y to a half, then the Fourier coefficient, Whittaker-Bessel function, solution of a differential equation of order 2, in the argument 2 pi and y, and the dependence on x is fully periodic exponential of 2 pi I nx. And you can write your AP as p to the minus a half plus times alpha p plus alpha p. Oops, what did I do? That's the trick, okay? And you can write it as AP is p to the minus a half, alpha p plus alpha p inverse. And then Ramanujan basically tells you that AP must be less than or equal to 2 p to the minus half. This is a weight 0 form. This is equivalent to alpha p being equal to 1. Now, Kim and Sarnak in 2003 gave us what it is now the best available estimate for these Fourier coefficients. You can write it in terms of AP as less than or equal to p to the minus a half, p to the 7/64 plus p to the minus 7/64. And in terms of alphas, it's equivalent to alpha being between p to the minus 7/64 and p to the 7/64. Now, this was done only over Q. I'm going to go over just a little bit of part of the proof of this, but the technology that goes into this is you have some input from the theory of L functions, automorphic L functions, some facts about their absolute convergence. You put it into a machinery which originally in some cases was done by Duke and Iwanish, and then you have to work through the methods of analytic number theory, and you will get this estimate. And they did it over Q. The issue is that you have to really look and work with the unit group of the field. So over Q, that's not hard. But when you go to other groups, that was a real issue. And Blomer and Bromley finally did it in 2011. So now this is the best estimate there is over any number field. So this 7/64. Now, the Archimedean version of this is the so-called Selberg's conjecture. Now, Selberg wants that this eigenvalue be bigger than or equal to a fourth for a congruent subgroup gamma. And what they did, using this same general philosophy, is they proved this 1/4. I don't know why it goes so far. I don't even touch it. You get this 1/4 minus 7/64 squared, which is it's a number with 7 digits, 0.2380371, which is pretty close to 0.25, but still far from it. That's the. I think I can now move. Any general progress in getting these estimates, short of really proving the Ramanujan, which nobody has any idea at the moment, is by using functoriality, transferring automorphic forms from GL2 to higher GLNs. And this is done through these symmetric powers. So a symmetric power representation of GL2C is a GLM, is an m+1 dimensional representation of GL2C on the space of tensors of rank M. And this was proved, the breakthrough that came, it was proved for M equal to 3 by Kim and myself, and then for M equal to 4 by Kim. Now, how do you, I want to explain, let me just, the results that Blomer and Bromley, let me, maybe it's better go to the, okay. What you really need to do, you really need to know the existence of symmetric fourth. To know existence of symmetric fourth, you have to take Regis squared of symmetric cube, which Kim proved. That's one of the cases that for GL4, he proved that Regis squared of symmetric fourth is automorphic. And out of that, you would get that sim squared of GL2, sim fourth of GL2. I mean, this decomposes, if you put sim cube, it decomposes as a 5-dimensional and a 1-dimensional, and the 5-dimensional is just sim 4 times omega pi, and the 1-dimensional is just omega pi to the 3. So the cube of the central character. Now, let me show how this, I mean, the automorphic input to this game is this theorem, or whatever you want to call it, proposition. It is that if pi is a cuspidal automorphic representation of GL2 of AF, so this is, I'm not going to do over any field, the argument is the same. It doesn't depend on the field. F is a number field. Then if you take symmetric squared of the symmetric fourth of pi, then this is an absolutely convergent function for real of s bigger than 1. Results like these are proved by Jacquet and Shalaika for Rankin-Selberg-Dell functions. And they are very deep. And so far, those are the basic ones. And we reduce everything to that, to these basic cases. So let me try to explain how this works. What Jacquet and Shalaika have is that if you take, we now know by Kim that sim 4 of pi is a automorphic representation of GL5 of AF. So we can use this Rankin-Selberg L functions. You look at L of S sim 4 of pi by itself, and then that can be written. We can check. There are incidental isomorphisms, and we can check that that's very well-known result. That's L of sim 4 of pi and CB squared. Let me, I mean, not everybody in this room is an expert in automorphic L functions. Let me just, Werner sort of explained that if you have a representation with some representation of the L group, then pi corresponds to is a tensor product. And if you take each pi v, and each pi v corresponds to a semi-simple conjugacy class, and rho is a representation of, so this is in GLNC for some n. Let me just make it general. And then you apply rho. Rho is a representation of GLNC. You apply rho to TV, and then you compute determinant of 1 minus rho of TV, then QV to minus S inverse, and then you multiply over all V. So you do, these other guys are defined the same way. You take sim squared is a representation of GL5, and veg squared is a representation of GL5. And you take these two L functions, that's the Rankine product L function. Now again, through this incidental isomorphisms, you can show that L of sim squared, let me see if I can. L of sim squared, veg squared of sim 4 of pi is equal to L of sim squared tensor omega applied to this 4-dimensional object, sim cube of pi, which is on GL4. Now, omega is a central character. Now, how do we control now? So it's clear that if you want to say something about sim squared, you have to say something about veg squared. And if you want to say something about veg squared, you have to say about that next L function. And that next L function, we don't know. So you go to this line below, and again, you use Jacquet-Shalaika's argument. You have this is equal to this times that. Again, you will get things about this one if you know things about the veg squared tensor omega times sim cube. In general, when I write some representation times omega, it's different from taking the representation and tensor it with omega. So one has to be careful with this. Now what do we have? What inputs do we have? We have that symmetric cube of pi is automorphic on GL4, and veg squared of symmetric cube of pi is automorphic on GL6. And then sim4 will be automorphic on GL5 as a result of these two facts. And then because of that, we noticed that this sim cube veg squared tensor omega is nothing but what Kim produced, veg squared of. Something is wrong with this machine. I mean, I'm really touching all the way off there. Okay, all right. I shouldn't use it. Just maybe my finger does the job. So that L function is equal to veg squared of sim cube tensor with omega, and this is just a Jacquet-Godemont L function, the standard L function of corresponding GL. And now we know that by Jacquet-Shalaika, we know, okay, this second L function is by Jacquet-Shalaika absolutely convergent. Then we go back. Then we go back and we divide out, because this is really this second L function which comes into the Rankine product L function of this thing. We know that now this thing is a representation, the H2 of sim cube of pi is a 6-dimensional representation, a representation of GL6 by Jacquet-Godemont. We know that, and in fact Jacquet-Shalaika, we know that this is absolutely convergent. Then we get the other one is absolutely convergent, and then we have the theorem. Now, I couldn't find this proof in your paper, and I looked at my notes later on, and I found a proof similar to it, but this just came out. I asked Blomer, do you have it in your paper? They didn't have it in their paper. But it is pretty straightforward. I mean, it's pretty straightforward. All right. Now, Ramanujan conjecture is a very, very important conjecture in all of number theories. I mean, to people who work in automorphic forms, we have the same story. The curiosity came when we started looking at other groups. For GLN, we definitely expect it to be true. And most of us have very little to say about it unless true functoriality, or these estimates that Luo, Rudnick, Sarnak have for general GLN. But beyond that, we don't have anything for GLN. So we look at an arbitrary group. We look at in fact, we noticed issues with even SP4 or GSP4. You look at an arbitrary group over a number field, so K is a number field. Now that we are working general, so I may as well take number fields. AK is the ring of adults. G is a quasi-split reductive group over K. I make this assumption because I'll be working with this within the conjectures I'm going to put out. We have a Borel subgroup. I mean, if you don't like a general group, think of GLN and think of upper triangulars. Or think of classical groups and again upper triangulars. Then I think Werner this morning talked about this L2 of GA over GK. There is some central character. I didn't write it there. I just tried to be brief. So you pick up a representation inside here. You assume it appears in the discrete spectrum. In fact, you assume it appears in the cuspidal part. Now, each pi v is an irreducible, admissible, unitary representation. Unitary representation of the G of KV. KV is the place. And we have this hypothetical Langlands group, L sub K. It's something which is not defined, but it allows you to formulate matters. And there is the L group. L group is just G check, semi-direct with this group. I mean, you can, in some sense, you can just use the way Deligne group, the usual one, if you don't want to be too broad in that sense. Now, then what would be the Ramanujan, as it was discussed, I think, yesterday with Lobotsky? Satake showed that the Ramanujan conjecture is equivalent to pi v being tempered. It's clearly the case in all the unramified primes, and there is no harm in assuming that it is true in general, and it is the case for, I mean, it seems to be the case at least for getting there for GL2, definitely for holomorphic forms. By Deligne it is over Q and over some number fields. But for general, this is not true. Well, I put it in this way that each pi v should be tempered. I repeat it again. As I said, there are this counterexample of Howe and Piotetsky-Shapiro and Sato-Kurokawa that it's not true for even SP4 or GSP4, but it is expected for GLN. So for GLN, you expect it to be true, and it would be a great happening if it is true, even for GL2. But we have very little doubt. Now, when it comes to classical groups, there is the recent work of Arthur. He wrote a long book now, 450 pages from that. And what he does, he transfers automorphic forms from classical groups to GLN, some appropriate GLN. And he does this by means of the trace formula, which Werner said some stuff about this morning. And where does it come from? You look at the L group of a classical group. I mean, it's either a SP or a SO. It sits inside some GLN. I'll assume this N is minimal. If you start with and then what Arthur says that you can start taking representation on L2 and try to lift them up to GLN. What one expects on GLN is that you pick up representations which are self-dual. You could have a cusp form on classical group, but it goes up and doesn't have to become cusp form. It could become just an Eisenstein series, just an automorphic representation. What we call an isobaric quotient of a representation of GLN basically means that this is the so-called classification theorem of Jacquet and Shalaika. You look at the GLN, you take a parabolic inside it, which is Levy is a product of GLN I's. You take these representations tau I's on there. You assume they are unitary cuspidal. Then they show there is a unique distinguished element which they call isobaric quotient of this, and it's written in this form, this box sum that you see. Now, in Langland's formulation of the Ramanujan, if you have a representation, and if it ends up, these are constituents of some induced representation, globally induced representation, and they have many other constituents. So Langland's formulation was that if your representation on any group, on classical group, ends up lifting to not one of these, but something else, which he called it anomalous. Then Ramanujan is false. And in case of Arthur, it seems to be really valid, what he does. Now, in the case of classical groups, which is his work, and then in the case of unity group, Mach has done it, he shows that this lift basically becomes, if you have something tempered in the meaning, which meaning of it I'm going to discuss a little bit later, the transfer is going to be of this form. It would be an isobaric sum, and tau i's would be in equivalent unitary Cauchy-Billout representations. Now, we did this before Jim for the so-called globally generic representations of the group, of the classical group. Now, the notion of a globally generic representation is just simply that this integral for some function in the space of representation is different from 0. U is the unipotent radical of that Borel. You evaluated that, you take its ak points and divide out by k points. That's a compact group. You pick a function phi, chi is a non-degenerate character of u, ak. You integrate, and you want it to be non-zero for some phi. If this happens, you call it globally generic. For GLN, everything is globally generic. For classical groups, no, that's not true. But there are very nice conjectures, some of which are not proved for classical groups. Now, one of the conjectures which came up way before this work was done is the so-called tempered L-packet conjecture. So what you do, Arthur in his work gives you L-packets. It decomposes the space of automorphic forms to partitions of representations, automorphic representations, which he calls L-packets. And there is the same thing over local fields. And the conjecture was that if you have tempered L-packet, which I will say more about it, then it will contain one of these guys. It will contain at least one globally generic representation. And it is part of his work that he proves this. He proves this, and there's also a local conjecture that he proves this. And this local conjecture was already, for real groups, it was in Vaughan's work. I conjectured it for p-adic groups, and now we have quite a number of cases. This needs our transfer, this needs this transfer, and needs also the descent of Ginsberg, Grallis, and Sudry from classical group, from GLN to classical groups. Now those elements, those representations of GLN, which are really image of this transfer, are always self-dual representations. So that's what this thing does. This particular conjecture has vast generalizations, but no longer, of course, for L packets, but for what I will discuss a little bit, A packets or Arthur packets. These are, Jiang started them, and he has some further versions with Liu and Savin. Now, I want to make a conjecture. Let pi be, if we take pi a cos form on, I should have said on G of AK, but it is on G, which is, G is quasi-split over K. Assume pi is globally generic, i.e. it has a non-zero Whittaker Fourier coefficient, then pi is tempered. Already for classical groups, the work that with Cogdell, Kim, and PS shows that it is true. But this has to be true in general. I'm going to produce some evidence and give some easier facts about it. Now, to address the issue of temperedness, we have to really look at the, versus non-temperedness, we have to look at what Arthur did. Arthur introduced in, maybe, when was it? In 1983 or 1982 in Maryland. He came up with this notion of Arthur packets. So an Arthur packet is a homomorphism from that Langnon's hypothetical group or the Weil group, Weil-Deligne group, cross SL2. So he added one extra copy of SL2 and to the LG. And it is basically given by a product of a function, a homomorphism from the L group to LG, which is the tempered part. That thing is bounded, or it is tempered. And rho is a complex analytic morphism. So this is that they are commuting. After all, those two groups are commuting with each other. So this is a commuting homomorphism. And so take one of these Arthur parameters. The idea is that everything, every automorphic form is parameterized by these objects. It is very precise. When you think about it, for example, complementary series don't have Arthur packets, don't have Arthur parameters. And they are not supposed to appear, even for SL2. So having an Arthur parameter automatically means that you should appear in the space of, you should satisfy, at least for GLN, you should satisfy the Ramanujan. So the tempered representations are parameterized by psi for which this rho is 1. So you only have the phi, which was the bounded parameter. So that is them. And let me write by psi of j Arthur parameters up to LG naught conjugacy. Now this is where I want to bring in the other parameter that Arthur introduced, and that will allow us to formulate that conjecture about the temperedness of globally generic representations. For any Arthur parameter psi, you can attach a Langlands parameter. Phi sub psi is a map then from the LK, from the hypothetical group, or if you don't want to go there, to the Lin Wei group, to LG defined in this way. W is psi of W, and this is an element in SL2C. You take the norm of W to 1. This is something in SL2Z, and you take effect of psi on that. So that gives you a homomorphism into LG. Now, as soon as you have one of these, then you have a Langlands packet. You're going to have a Langlands packet. And let me tell you some facts about these two objects. The A packets are very hard to find. On the other hand, the L packets are a lot easier. If you know the packets for the tempered parameters, then using the Langlands classification, you can take the packet for the I will explain it in a moment, for the whole L packet. Now, those elements in the L packet phi psi, which supposedly we can find much easier than the A packet, those are supposed to be the most non-tempered elements of the A packet. So in these sets that Arthur gives you, in this or in general, they are supposed to give you the most non-tempered objects. And another thing which is very easy to check, it's just complex Lie groups, is that this mapping psi going to phi psi is an injection. There will be a lot of Langlands parameters which won't come from an Arthur parameter. It also says that Arthur parameters are rather specific. It says, in some sense, that if you know this Langlands packet, you would know the Arthur packet. It's not that easy at all. It's a lot of work. So that's the... Now, let me go to the conjecture that I think is easier in some sense, that the whole thing, or at least give us some way of attacking the other conjecture of me. Suppose I take a local field K and assume G is quasi-split, and assume this Langlands packet pi sub phi sub psi has a generic member in it, something which has a Whittaker model. This is local, so you don't have to look at an integral, just the existence of a Whittaker functional. Then phi psi is tempered. And this we can prove in many cases, so it's really in a very good shape. The second one is the global one. The global one is much more serious. K, this is the thing which has a lot of things to. Let K be a global, the number field, G equals a split. Assume you write your representation automorphic form as this tensor product, and assume it is globally generic, so that integral, that period doesn't vanish on it. Then each pi v, if you take one of these, if you look at one of these, am I in the right place? No. Okay. Assume you take you take a representation pi v inside this pi. If you take a representation which is globally generic, I claim then that each of the local components are really not only in the Arthur packet, but in this smaller Langlands packet. Now, if you know this, then by conjecture 1, you're going to have that conjecture that all the globally generic representations are tempered. Now, how do you address such a thing? First of all, let me go to the second comment here. If you have a globally generic representation, it means that basically there is a period integral which is non-vanishing. So the question is whether the non-vanishing of a period integral can be related to issues that Arthur brought up. I think Venkatesh and Sakellarides, they have some conjectures on periods, connecting them to Arthur parameters, but I haven't carefully checked that. There is also the work of Jiang. Lapid and Mao have some conjectures about globally generic representations. So, and I'm sure there are more. Putting these things together, we must be able to say something about the conjecture B. So then really the question is that how does the existence of this period, the non-vanishing of this period, narrows down Arthur parameters? And there are, of course, the relative choice formula of Jacquet to do that, but these are all pretty. Now, there is a lot of progress made towards the local conjecture. In cases of classical groups, it was first proved by Born and Beiying Liu. Using local, they eventually used the local representation theory and also local Langlands conjecture in the cases that they do work with. Now, the local Langlands conjecture in the cases, first of all, for SO odd, it was done by Jiang Sudri and then Harris Taylor. Of course, that's before. Harris Taylor, Henyard, and now Schultz have a proof for the GLN. Arthur now gave a proof as a result of his work for classical groups. Now, let me address the problem of how one can reduce doing the conjecture A, the local one, to a question in local Langlands correspondence. But I will formulate it. It's very general. You can do it for any group. Now, suppose that G is a quasi-split group over a local field, real or p-adic. Let me start with an Arthur parameter. Let me take the Langlands parameter phi sub psi there. If you take this is usually a non-tempered parameter. So if I have a representation pi in this L packet, then pi is basically a Langlands quotient of an induced representation. Usually write it like this. As you can see, tau will be a tempered representation on MK. Nu will be a complex parameter on the positive Weyl chamber. It has to be there, so you get a unique quotient. Your parabolic is Mn. Now, as tau ranges on over its L packet, then these little pi's, which are these Langlands quotients, will range over the L packet inside pi of phi psi. So that's how you get how you get a non-tempered L packet from a tempered L packet. It's as easy as this. Of course, you have to know what's the elements in the non-tempered one. Let me write tau sub nu as tau tensor nu. And let me take R to be adjoint action of Lm on Ln. Ln is the Lie algebra of Ln. And then we have these L functions defined in general. This L of S, tau sub nu and R. It is attached to a data. Data would be Gm and this tau nu. In a paper in Kyoto Journal, I proved the following theorem. Assume that you have assume this pi phi psi has a generic member. Now, with this notation, we discussed phi psi is basically given by this tau nu. That's the local Langlands correspondence. After all, it's going to factor through M, through Lm, because it's induced from M. So phi psi really also gives you the packet of tau, so tau nu. Now, assume that we have the local Langlands in the sense that our thin L functions are equal to those L functions that I defined. So L of S, R composed with phi psi, is same as L of S, tau nu, and R. So this side were defined by the methods of harmonic analysis. The other side is the L functions defined by Artin, Artin's recipe. If this is true, then phi psi is tempered. Then that rho is equal to 1. Now, the proof uses a joint work of Lee and Castleman. We published in Annals Scientific, I think. When is it? 1998 or something. Now, what are the corollaries that we get out of this? If K is equal to reals or complex, so Archimedean, G arbitrary, this is true. That conjecture A is true. N equals split group, an Archimedean field. K periodic and the element generic member spherical. G arbitrary equals a split, again, it is true. For classical groups and G spin groups, it is true. You have to use some, there is one L function, which is annoying. There are two L functions which appear. They are L functions of Rankine products and the L functions of symmetric square and wedge squared. Hanyard showed that these wedge squared and symmetric square L functions are equal to the Artin ones. So we have that. For those other ones, we use these lifts that we have, these lifts of CK, PSS, and the lift of, or KK. Of course, that is not really, these guys haven't addressed that. But then there are also these lifts that Askari and I did. So the conjecture is valid for all these G-spin groups and classical groups. Now, exceptional groups. When we go to exceptional groups, for G2, conjecture is fully valid. There is no problem, because the L functions are completely to control. F4 is an interesting group. For F4, there is one L function. When the derived group of the LM is a sp6c or a spin 7c. In this case, you get that the spinor L functions. And I don't know if none of the works that has done by Arthur and others won't answer anything like that, because this thing, as you can see, will not factor through SO7C. It's a genuine L function for LM. Now, I can't do that. But for exceptional groups, EN, let's take the case when M derived is SLN. So you just remove the node outside, and then you're going to pick up as your Levy modulo the center, you'll pick up SLN6, SLN7, and SLN8. The L function that shows up is the exterior cube of the representation. And in this case, I have restrictions, so I had to reduce myself, as I will discuss in the next section. I had to reduce myself to the case when for exceptional groups, the supercuspidal representations are monomial. That will say that if you are in E6, stay away from 2 and 3. You are in E7, stay away from 7. And you are in E8, stay away from 2. Then again, in these cases, the conjecture is valid. So there is quite a bit of evidence that this local conjecture is true. So hopefully, if we have the local conjecture and we have some idea from the help of people who work on periods, or maybe this will also give them some ideas for other things, and relating them to this Langlands parameter phi psi, we may be able to answer this thing in rather general. The nice thing about this is that this is an internal proof. Arthur's proof, Arthur's work leads to something like this, but he has to go to GMN. And he has to, of course, at the end, assume that the Ramanujan for GLN. But beside that, this will give you an internal proof. For classical, for exceptional groups, you have no other group to go to. You go from F4 to E6. That doesn't do you any good. Now, let me go to the last section of this talk. This was something that I would have talked about if this wasn't for his birthday, for Peter's best birthday, but I think what I talked about is such a fun. I like the Ramanujan conjecture. But I want to quickly go over this new paper we posted, and I think in some sense, maybe this part would be your birthday gift. And this is that if you look at the GLN, and you look at these L functions, exterior square and symmetric square, and try to see if they are arithmetic to the local Langlands correspondence. We finally finished proof of it, and we posted in arXiv about 2-3 weeks ago. It took us a long time for one part of it, which is very technical, but now we have it. Now, so the problem is that you take a local field, periodic, real, or complex. In real and complex, this thing is answered already in my 1985 Duke paper, so we know that. But take it periodic, the Weil group WF, you have a n-dimensional continuous Frobenius semi-simple representation for W prime of f. You have an additive character, psi. You have these epsilon factors and L factors of Artin, and you define them. There are the recipes for that. And then you also have the local Langlands correspondence. Rho going to pi of rho, as established by Harris, Taylor, Henyard, and now Schultz. And they have the property that they match the Rankin product objects, the root numbers and the L functions. And this is proved now. We have several proofs of it, so you're on solid grounds. What we proved is this. Let me take epsilon to be the root number. I define this using the triple that we choose for this paper. There are several triples. The triple that we choose in this paper is GSP2n, GLN, and a triple, and then the representation, pi of rho or whatever, pi. Now, this is the group. This is the Ziegler-Levy inside the group. And we look at this triple, and out of this triple, you define these local factors. You define local coefficients, and you define gamma factors coming out of that. So for this triple, through one of, they all, I mean, there's a uniqueness. So no matter what, you can also use SO2n and GLN, but that is a disconnected group, and n is odd. And that's a headache. So you stay away, but you use this one. You get two objects. One is the standard L function for GLN, and the other one is this L function wedge squared. You prove everything for wedge squared, because sim squared follows from the matching of the Rankin-Selberg objects, products. Now we have this epsilon, I defined it, and the L, and then the same thing for symmetric squared. And these are the factors defined by harmonic analysis. And then we also have the Artin factors. And the theorem is that these are equal. The L function was already proved by Henyard, I think several years ago, but he made it very clear that you cannot prove the root numbers without using stability. And we did prove stability through it's a nice argument, I'll explain it. Now, proving stability is very hard. Stability means that you take these gamma factors, you can twist them by a highly ramified character. If you assume two absolutely different representations, only sharing a central character, you twist them by highly ramified characters, the factors become equal. This is called the stability. Piatetsky and Kagdar and Piatetsky used this when they were studying classical groups, and they gave us some way of going through, but that was really good for the cases of functoriality. This case is much harder. This case is way harder than that. So what we did a trick of reducing to try to answer the stability only for supercuspidals rather than a general representation. General representation, there is little technology in this setting. Now, what you do, you show that the gamma functions are equal. So gamma is usually epsilon L of 1 minus S contra gradient divided by all of S. Now, this is the argument. This is a very robust argument. It works for any kind of theory of L function. It doesn't have to be Langlands-Shahidi or anything. It works comparing Artin with this or two different methods with each other. So what we did, we first proved the existence of a base point, a irreducible representation rho naught, and a supercuspidal representation pi naught, which they come through local Langlands. So we proved that should be a rho naught. That should be a rho naught. Gamma of rho naught tensor chi matches gamma of pi naught tensor chi. And then in the left-hand side, Deligne tells us that if you make this chi to be highly ramified, you can have it for any rho, supercuspidal, irreducible. So we had that. In fact, you can do it for any rho. In the other side, in this side, this is the hard part. If you show the same thing, that you have analytic stability, meaning that these two factors on the right are equal, then you have the equality of gammas. As soon as you have the equality of gammas, you have everything. Everything follows. There are recipes. So what you do when you prove that, you have the so-called global, the so-called stable equality of these factors. Now, you can extend it to all rho, not just the irreducible ones, through the so-called multiplicativity. Then there are these ideas of Harris and Henyard. You take a local global argument, and you show that you have the thing for monomials. Then you use Brouwer's theorem and this identity, and you get it in general. So this is how, so the real as Peter says, the beef is here. Ah, beef doesn't want to come. Ah, anyway. The beef is in that arrow, the right-hand arrow. You have to prove that equality, that these two things are equal with each other. And what we do, the problem is that what you have to do, you have to look at the so-called partial Bessel functions. You start with a function f cc infinity of omega pi, meaning that it's a function of compact support mod center, changes according to the central character omega pi, and you look at the integral of this. Now I'm just going to do it on the big cell, WL. WL is the long element of the GLN, second diagonal ones. A is something in the diagonal. I don't know why that should be UAK over UK. It's another typo. Not UK, that should be just UK. I don't know, divided by a stabilizer. I think I didn't catch these things. That integral is just a local integral. So it's over the upper triangulars, or divided by some stabilizer, if there is one. And then there is the cutoff function. That's the problem. Cutoff function is U2 transpose A prime U2. A prime is just you make the first coordinate of the diagonal equal to 1. You divide it by center, and you just split that map. So this is the so-called partial Bessel functions. Bessel functions are very nice. If you didn't have that phi there, that would have a very nice germ expansion that Jacquet and Ye proved some time ago, and we were hoping to use that. But this one is much, much more nastier. Now, if you have a representation pi, you take a matrix coefficient of it, it would be that f. How do we prove this? You just, some facts about the Weyl group elements. You have the broad ordering. You have two elements in the Weyl group are in the broad order. First of all, let us suppose that, meaning that they are in the same broad order if the broad cell of one appears in the closure of the broad cell of the other one, in the boundary of the broad cell of the other one. And then you assume that W supports a Bessel function. That simply means that W can be written as a long element of the group times long element of the Levy subgroup. And then we take the AW is just the center of the corresponding M, and then we decompose that. This is what Jacquet and Ye has in their papers. We produce a transverse torus, AW prime W, and then we define omega W. That's a sum over all the W prime bigger than or equal to W, C of W prime. Now, it's open in G with C of W closed in it. Then we need this asymptotic expansion, and this took us about a year and more to prove. And we benefited from Jacquet and Ye proof, but we couldn't use it directly. You look at this Bessel, partial Bessel function. You can write it over each of the things in the boundary of the long element. So everything is in the boundary, but not everything supports a Bessel function. So you're going to have a full sum over the elements in the boundary. And this satisfies some conditions. The gamma function that you want is basically a Mellin transform of this. It's a Mellin transform of this partial Bessel function. Now, if you have a statement like this, if you have this expansion, and if you can show this first term only depends on the central character. These other ones depend on the representation, but they are uniformly smooth. And then you have an integral. You take two of these, two representation, pi 1 and pi 2. You take the difference. That's the integral. Since the part depending on the central thing went away, the non-smooth is gone away. You have a smooth function against a character, and the smooth function is uniformly smooth. That thing is 0, so they are equal. And that's the argument. So that shows that you have the stable a stable equality of the factors, and then the machinery that I mentioned will do it in general. So the real hard work beside that general, that was a nice, robust argument we had, but we had it 3 years ago. But this one took us a year and a half to prove, and we got really, now we have it. And so we know these other factors are equal. And of course, there are many other factors, but we don't even know how to define them. I have some ideas about the exterior cube for GL 6, 7, and 8. I think some of these ideas work there, but we don't have anything beyond that. Well, I think I conclude. I have gone 3 minutes over. Happy birthday, Peter.
Well, thank you so much for the great talk. Any questions?
Thank you. Sorry, I don't understand the examples of SP4 and GSP4, but I still have the question that what would be the geometric assumptions on the reductive group which would imply truth of Ramanujan if we want to stay away of analytic
I
assumptions?
mean, any group but GLN, you will have this thing false. So pick your criteria. Only for GLN, we expect it to be true.
No, I mean, you have counterexamples. Can you make them, do you have a geometric?
They are Siegel modular forms,
Right.
but they are not, they are not locally, they are not globally generic. They are just the holomorphic forms.
Okay.
These globally generic ones are not holomorphic.
Okay.
Okay, so they are holomorphic forms. But there are holomorphic forms which are tempered. So they are.
Zhenshu Li and I guess Berger and myself many years ago made constructions in exceptional groups where you're now treading
Yes.
to make conjectures, and Arthur says nothing about that.
No, Arthur, this
So the question is, have you ever checked where these non-tempered examples we make, whether your conjectures are valid on them?
I know of your results, but I was thinking of this conjecture 2 months ago. So this
No,
is
I'm just saying,
No, I haven't,
are
and
these
I
things
will.
consistent? I mean,
I
because we
think
have
that-
examples, so you better,
No,
they better pass, your conjecture better pass those.
I think it will pass. I will check it, but I
okay.
think it will pass. I'm pretty confident about this conjecture.
Okay. We probably have time for one more question. Yeah.
Yes, that's true.
Exceptional groups of non-tempered which aren't like G.
No, you did it. Yeah, I know. I will check it.
Look at many examples.
Yeah, no, I'll look at them.
Could we have one more question? Okay, no, okay. So let's thank Fridun again. So let's resume in 5 minutes.